So this is another example of using Vsepr theory to predict the shape of a molecule. The example this time is CH2Cl2, so 1 carbon, 2 hydrogens, 2 chlorines. So which one is the central atom, which is the one that has the most lines coming off it, and how do we figure that out? Well, the trick is to remember that carbon is in group 4. So if it's in group 4, it makes 4 covalent bonds to fill its valence shell with electrons. So it's going to have 4 lines coming off it. And it's no coincidence that you've got 2 hydrogens and 2 chlorines to complete this molecule. So also, hydrogen always makes 1 bond, chlorine always makes 1 covalent bond. So that should hopefully help you figure out the actual arrangement. So I'm going to go straight to the line diagram and skip the Lewis dot diagram for this. But if you wanted to draw the Lewis dot diagram, I'd definitely recommend that. So what I'm going to do is just pretend that I don't know anything about this molecule, and all I'm doing now is just drawing the 4 bonds on there, and that's all I know so far. I don't know about this being a tetrahedral, even though I really think it is. But anyway, so I'm going to just draw this and hope for the best right now. One thing to remember here is that chlorine does have lone pairs of electrons. So this is 1 bond, so this is 1 electron from the chlorine, 1 from the carbon, so that means this will have 3 lone pairs, and so will this one. So it's always a good idea to include the lone pairs, even if these aren't really influencing the shape of this molecule right now. Always include them, really good habit to get into. Right, so I've drawn my shape. So my next step is to count the number of electron areas. And this is nice, 1, 2, 3, 4. So 4 electron areas. I go to my table, my little cheat sheet. I also know that there's 4 bonded pairs of electrons. There's no lone pairs, so that really narrows it down. And if you check your table, the cheat sheet, then this is clearly a tetrahedral structure. So I'm going to erase this, or parts of it, because I know how to represent a tetrahedral shape now, because I watched the last video. So all these 4 bonds aren't in one plane. So I've got to draw like in 3D, if you will. So this is the 3D version of dichloromethane, which is this molecule. So the bond angles for a tetrahedral are 109.5 degrees. And I'm done. I don't have the shapes with me, but if I did, you'd see that this is very similar to methane. Silicon is also in group 4, and that would make a very similar shape of molecule. So as another trend from the periodic table is that elements in the same group exhibit the same bonding properties, and so silicon would actually make a very similar structure to this. And that's true for oxygen and sulfur. They both make similar shapes. If you remember H2S from the previous video, identical to H2O. Chlorine, fluorine, bromine, iodine, all the elements in group 7, they all make very similar shapes, usually linear. If you imagine HCl, if you've only got 2 atoms like this, it can only go one shape, and that's linear. So that's another example of how you use Vsepr theory to predict the shape of a molecule. If you have 0 lone pairs, the only repulsion that you have is between bonded pairs. And remember that if, rather than have the 4 bonds at 90 degrees, if we did that, there'd actually be less room. It wouldn't be an even amount of room or space between each bonded pair. So this would actually allow all of the bond angles to be 109.5. So that's it.